Hi everyone, welcome back to the Comptia Network Plus course, Forward and Filter Decisions. When a frame arrives at a switch interface, the destination hardware address is compared to the forward filter MAC database and the switch makes a forward filter decision. In other words, if the destination hardware address is known, listed in the database, the frame is only sent out the specified exit interface. The switch will not transmit the frame out any interface except the destination interface. Not transmitting the frame preserves bandwidth on the other network segments and is called frame filtering. But as I mentioned earlier, if the destination hardware address isn't listed in the MAC address database, then the frame is flooded out all active interfaces except the interface on which the frame was received. If a device answers the flooded frame, the MAC database is updated with the device's location, its particular interface. So by default, if a host or server sends a broadcast on the LAN, the switch will flood the frame out all active ports except the source port. Remember, the switch creates a smaller collision domains, but it's still one large broadcast domain by default. In figure 11.7 you can see host A sending a data frame to host D. What will the switch do when it receives the frame from host A? If you answered that's because host A's MAC address is not in the forward filter table, the switch will add the source address and the port to the MAC address table and then forward the frame to host D. You're halfway there. If you also came back with if host D's MAC address was not in the forward filter table, the switch would have flooded the frame out all the ports except for port FA0/3. Let's take a look at the output of show MAC address table command as seen from a Cisco Catalyst switch. The MAC address table works pretty much exactly the same on all brands of switches. So switch hash sh MAC address table VLAN1 MAC address 0005.dccb.d74b type dynamic FA 0/1 1000.f476.9e80 dynamic FA0/3 1000AF4679E8B dynamic FA0/4 1000A.f467.9E8C dynamic FA0/3 100.10.7B7F.C2B0 dynamic FA/3 10030.80DC.460B dynamic FA/3 10030.94.92.A5DD dynamic FA0/1 100D0.58AD.05F4 dynamic FA0/1. Now suppose the preceding switch receives a frame with the following MAC address: source MAC 0005.dccb.d74b. destination MAC 000A dot F 467.9E8C. How will the switch handle this frame? The right answer is that the destination MAC address will be found in the MAC address table and the frame will be forwarded out FA0/3 only. Remember that if the destination MAC address is not found in the forward filter table, it'll forward the frame out all ports of the switch looking for the destination device. Now that you could see the MAC address table and how switches add hosts addresses to the forward filter table, how do you stop switching loops if you have multiple links between switches? Let's talk about this possible problem in more detail. Loop avoidance. Redundant links between switches can be a wise thing to implement because they help prevent complete network failures in the event that one link stops working. But it seems like there's always a downside. Even though redundant links can be extremely helpful, they often cause more problems than they solve. This is because frames can be flooded down all redundant links simultaneously, creating loops as well as other evils. Here are a few of the problems you can be faced with. If no loop avoidance schemes are put in place, the switches will flood broadcasts endlessly throughout the internetwork. This is sometimes referred to as a broadcast storm. In real life, it's often referred to as less polite ways that were not permitted to repeat in print. Figure 11.8 illustrates how a broadcast can be propagated throughout a network. Pay special attention to how a frame is continually being flooded throughout the internetwork. Physical network media. One way to test loop avoidance operations of your switch is to plug one end of a cable into one port, on the other end of the same cable into another port. If loop avoidance is not operational, this should cause a big broadcast storm. What you see in figure 11.8 is that a device can receive multiple copies of the same frame because that frame can arrive from different segments at the same time. Figure 11.9 demonstrates how a whole bunch of frames can arrive from multiple segments simultaneously. The server in the figure sends a unicast frame to another device connected to segment 1. Because it's a unicast frame, switch A receives and forwards the frame and switch B provides the same services. It forwards the unicast. This is bad because it means that the destination device on segment 1 receives that unicast frame twice, causing additional overhead on the network. So here you can see in figure 11.8 we have a broadcast storm. Switch A broadcast switch B segment 1, segment 2. Multiple frame copies. Figure 11.9 segment 1. Segment 1, unicast switch A, switch B, segment 2. You may have thought of this one. The MAC address filter table could be totally confused about the device's location because the switch can receive the frame from more than one link. Worse, the bewildered switch could get so caught up in constantly updating the MAC filter table with source hardware address locations that it might fail to forward a frame. This is called trashing the MAC table. One of the nastiest things that can happen is having multiple loops propagating throughout a network. This means you end up with loops occurring within other loops, and if a broadcast storm happened at the same time, the network wouldn't be able to perform switching at all. All of these problems spell disaster or something like it, and are decidedly ugly situations that just must be avoided or at least fixed somehow. That's where spanning tree protocol comes into the game. It was developed to solve each and every one of the problems. Distributed switching in a virtual environment such as you might find in today's data centers. Not only are virtual servers used in the place of physical servers, but virtual switches, software based, are used to provide connectivity between the virtual systems. These virtual servers reside on physical devices that are called hosts. The virtual servers can be connected to a physical switch to enable access to the virtual servers from the outside world. One of the unique features of these virtual switches is the ability of the switches to span multiple physical hosts. When this is done, the switch is called a distributed switch. This provides connectivity between virtual servers that are located on different hosts, as shown in figure 11.10. Spanning tree. Once upon a time, a company called Digital Equipment Corporation, DEC, was purchased and renamed Comptia. But before that happened, DEC created the original version of spanning tree protocol, STP. The IEEE later created its own version of STP called 802.1d. 802.1d. Yet again, it's not all clear skies by default. Most switches run the IEEE 802.1d version of STP, which isn't compatible with the DEC version. The good news is that there is a new industry standard called 802.1w, which is faster but not enabled by default on any switches. To begin with, STP's main task is to stop network loops from occurring on a network layer 2 on your layer 2 network bridges or switches. It achieves this feat by vigilantly monitoring the network to find all links and make sure that no loops occur by shutting down any redundant ones. STP uses the spanning tree algorithm STA to first create a topology database and then search out and destroy redundant links. With STP running, frames will be forwarded only on the premium STP picked links. Switches transmit bridge protocol data units BPDUs at all ports so that all links between switches can be found. STP is necessary in networks such as the one shown, figure 11.11, a switched network with switching loops. Spanning tree ports. The ports on a bridge or switch running STP can transition through 5 different states blocking. A blocked port won't forward frames, it just listens to BPDUs and will drop all other frames. The purpose of the blocking state is to prevent the use of looped paths. All ports are in a blocking state by default when the switch is powered up. Listening. The port listens to BPDUs to make sure no loops occur on the network before passing data frames. A port in listening state prepares to forward data frames without populating the MAC address table. Learning. The switch port listens to BPDUs and learns all the paths in the switched network. A port in learning state populates the MAC address table but doesn't forward data frames. Forward delay is the time it takes to transition a port from listening to learning mode. It's set to 15 seconds by default. Forwarding. The port sends and receives all data frames on the bridge port. If the port is still at designated or root port at the end of the listening port, it enters the forwarding state. Disabled. A port in the disabled state administratively does not participate in the frame forwarding or STP. A port in the disabled state is virtually non-operational. Switch ports are usually in either the blocking or forwarding state. A forwarding port is one that has been determined to have the lowest best cost to the root bridge, but when and if the network experiences a topology change because of a failed link, or when someone adds a new switch into the mix, you'll find the ports on a switch in the listening and learning states. As I mentioned, blocking ports is a strategy for preventing network loops. Once a switch determines the best path to the root bridge, all other redundant ports will be in blocking mode. Blocked ports can still receive BPDUs. They don't just send out any frames. If a switch determines that a blocked port should now be the designated or root port, say because of a topology change, the port will respond by going into listening mode and check all the BPDUs it receives to ensure that it won't create the loop once the port goes back into forwarding mode. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.